1. What specific problem does ASI-ARCH aim to solve in neural architecture discovery, and why is this significant in the context of AI research?
ASI-ARCH aims to solve the bottleneck in neural architecture discovery, caused by the limitations of human cognitive capacity, which restricts the pace of AI research despite advancements in computational power. This is significant because traditional neural architecture search (NAS) methods are constrained to human-defined spaces and often act merely as selection algorithms, failing to innovate autonomously. By leveraging the capabilities of large language models (LLMs), ASI-ARCH transcends these limitations, enabling AI to autonomously hypothesize, implement, and validate novel architectural concepts. This paradigm shift not only enhances the efficiency of architectural exploration, but also establishes a scalable framework for scientific discovery, allowing for breakthroughs that can systematically surpass human intuition. Ultimately, ASI-ARCH represents a critical step toward achieving artificial superintelligence for AI research, fundamentally transforming how AI systems can evolve and innovate independently.
2. How does the ASI-ARCH framework work? Please illustrate its methodology step by step, including the roles of the researcher, engineer, and analyst modules.
The ASI-ARCH framework operates as a closed-loop system for autonomous architecture discovery, structured around three core modules: researcher, engineer, and analyst. First, the researcher module proposes novel architectures based on historical data and human expertise, utilizing a candidate pool of top-performing architectures and employing a two-level sampling approach to ensure diversity and innovation. Next, the engineer module conducts empirical evaluations by implementing the proposed architectures in a real-world coding environment, where it iteratively revises its code based on feedback from training runs, ensuring that promising designs are not discarded due to simple errors. Finally, the analyst module mines experimental insights by analyzing performance metrics and comparing them with historical data, providing valuable feedback to inform future design proposals. This collaborative process allows the framework to continuously learn and improve, ultimately leading to the discovery of state-of-the-art architectures.
3. Can you provide a simple example to explain how the ASI-ARCH system discovers a novel architecture? Walk through the main steps of the algorithm using this example.
The ASI-ARCH system discovers a novel architecture through a structured, closed-loop process involving three core modules: researcher, engineer, and analyst. For example, let's say the system aims to create a new attention mechanism. First, the researcher module proposes a novel architecture based on historical data and insights from previous experiments, ensuring it is both innovative and distinct from existing designs. Next, the engineer module implements this architecture in a real-world coding environment, where it undergoes training and evaluation. If the training encounters errors, the system captures the error logs, allowing the engineer to revise the code iteratively until successful. Finally, the analyst module evaluates the performance of the new architecture, combining quantitative metrics and qualitative assessments to determine its fitness, thus completing the cycle and informing future design proposals. This iterative process enables ASI-ARCH to autonomously explore and validate new architectural concepts effectively.
4. What are the theoretical and practical benefits of using the ASI-ARCH method compared to traditional neural architecture search methods?
The ASI-ARCH method offers significant theoretical and practical benefits over traditional neural architecture search (NAS) methods. Theoretically, ASI-ARCH transcends human-defined search spaces by autonomously hypothesizing and implementing novel architectural concepts, which allows for genuine innovation rather than mere optimization of existing designs. Practically, it operates as a closed-loop system with a modular framework that includes a researcher, engineer, and analyst, enabling a comprehensive and efficient architecture discovery process that reduces the time and computational resources typically required for human-driven design efforts. Additionally, ASI-ARCH establishes the first empirical scaling law for scientific discovery, demonstrating that architectural breakthroughs can be scaled computationally, thus transforming research progress from a human-limited to a computation-scalable process. This contrasts with traditional NAS methods, which often act as sophisticated selection algorithms and are constrained by predetermined building blocks, leading to prohibitive computational costs and limited exploration. Overall, ASI-ARCH not only enhances the efficiency of architecture discovery, but also expands the potential for architectural intelligence beyond human intuition.
5. How is the performance of the proposed architectures validated in the ASI-ARCH framework? Specify the experimental design, datasets used, and metrics for evaluation.
The performance of the proposed architectures in the ASI-ARCH framework is validated through a two-stage exploration, then verification strategy. Initially, 1,773 explorations were conducted using models with approximately 20 million parameters, consuming around 10,000 GPU hours, to identify promising candidates that outperformed the DeltaNet baseline in both loss and benchmark metrics. In the verification stage, these candidates were scaled to 340 million parameters and trained on 1 billion tokens for rigorous validation, with the top-performing models subsequently trained on a 15 billion token dataset for comprehensive evaluation. The evaluation metrics included quantitative assessments of benchmark scores and loss performance, alongside qualitative evaluations by an LLM as judge, which considered architectural complexity, computational efficiency, and novelty. This rigorous experimental design ensured that the architectures not only met performance standards, but also contributed innovative advancements in neural architecture design.
6. What specific results were achieved by the ASI-ARCH method, particularly in terms of the number of discovered architectures and their performance against baseline models?
The ASI-ARCH method successfully discovered 106 novel, state-of-the-art linear attention architectures after conducting 1,773 autonomous experiments over approximately 20,000 GPU hours. In the initial exploration stage, 1,350 promising candidates were identified that outperformed the DeltaNet baseline in both loss and benchmark metrics. These candidates were then scaled up for rigorous validation, resulting in 106 architectures achieving state-of-the-art results. For final validation, 5 top-performing architectures were trained at 340 M parameters on 15B tokens, demonstrating superior performance against DeltaNet, gated DeltaNet, and Mamba 2 across various benchmarks. This achievement underscores the effectiveness of the ASI-ARCH framework in advancing neural architecture discovery.